Hello, my name is Jagan Loftus, and today I am going to explain how a turbocharger works. I am here at JTech, Jones Technical Institute in Jacksonville, Florida, and alright, here we go. Well, first off, I guess I should explain what a turbo does. A turbo has a turbine. It's turbine-driven forced induction. Forced induction meaning that it's pushing more air into the combustion chamber. That which is a far improvement over a naturally aspirated engine. Needing more air equals more power, more force to push out and to get equal power. Okay, so now there is a difference between a turbocharger and a supercharger. The supercharger is mechanically driven by the engine connected through a belt and a crankshaft, where a turbocharger is driven by the engine's exhaust gas. And we got an example right here. Charger, turbo. There's your turbine in the middle there. And that turbine is going to spin and force more air into your combustion chamber. And this one is a twin. It's got two on the sides. In normally aspirated piston engines, intake gases are pushed into the engine by the atmospheric pressure, filling the volumetric void caused by the downward stroke of the piston, bringing all the air into your combustion chamber, similar to a liquid drawing in a syringe. The amount of air actually inspirated compared to the theoretical amount if the engine could maintain atmospheric pressure is called volumetric efficiency. The objective of a turbocharger is to improve an engine's volumetric efficiency by decreasing density of natural intake gas, allowing more power per engine cycle. The turbocharger's compressor draws in ambient air and compresses it before it enters the intake manifold at increased pressure. That's where this would happen, right here. All this is compressing that air, getting real tight, real small, thanks to that turbine right here. It draws in ambient air and compresses it before it enters the manifold at an increased pressure. This means a greater mass of air entering the cylinders on each stroke. That's more compression. That's a bigger explosion, more power. It can also be used to increase fuel efficiency, like on a lot of diesels. It has to have a turbo or it'd be running around, getting low on the actual gas that's needed. Fuel, excuse me. In automotive application, the boost refers to the amount by which intake manifold pressures exceeds atmospheric pressure. This is a representative of extra air pressure that is achieved over what would be achieved without forced induction. The level of boost may be shown on a pressure gauge, usually in bar, PSI, or possibly kPa. In aircraft engines, turbocharging is commonly used to maintain manifold pressure as altitude increases. Since atmospheric pressure reduces as the aircraft climbs, power drops as a function of altitude in normally aspirated engines. Systems that use a turbocharger to maintain an engine's sea-level power output are called turbo-normalized systems. In petrol engine turbo applications, boost pressure is limited to keep the entire engine system, including the turbocharger, inside its thermal and mechanical design operating range. Overboosting an engine frequently causes damage to the engine in a variety of ways, including pre-ignition, overheating, and overstressing the engine's internal hardware. Now, you don't want to take one of these apart without knowing how to put it back together. There's a lot of timing. Here we have an example of a twin turbo. You got the turbo up top that's a little bit smaller than the turbo that's down at the bottom. Now what's going to happen is it's going to take in the air from the bigger turbo, compress it as much as it can, and then throw it into this smaller turbo, compress it even more, and then throw that into your induction system, thus creating more power. Twin turbo for the win. Now, as you can see, there's multiple sizes of turbos. We've got smaller, all the way up to about this size. Huge, big turbos for your diesel. Look at the turbine inside. That's what compresses the air, giving you more power.